we're going to explain the u-substitution. The u-substitution in calculus is a method where if we have a complicated integrand that we're integrating, for example, integral of some integrand with respect to x or something else, we make a substitution and we completely change the letters inside. We make a substitution. For example, we can change them from x to u. This is why it's called the u substitution. What we pick for the letter u is very important. It makes the difference between being able to integrate and not being able to integrate. Let's do some examples so this will make sense. First example that we're going to do is this one, 201. In example 201, we're integrating 4x over x squared plus 19 with respect to x. So it would be to our benefit to get rid of x squared plus 19 denominator. Let's call it u. Let u equal x squared plus 19. But when we get rid of x squared plus 19, we also need to get rid of the dx. Okay, so let's put this in red brackets. Make sure you get rid of x and dx. Let u equal x squared plus 19. The derivative of u with respect to x is 2x. To get rid of dx, rearrange this, so solve for dx. So dx equals du over 2x. This is dx. Go back to the integral. You have the integral of 4x over x squared plus 19, which is u dx. dx is du over 2x. Okay, this x and this x will cancel. 4 and 2 are numbers, take them out, and that leaves us with 1 over u. Integral of 1 over u. 4 over 2 is just 2. So this is 2, and the integral of 1 over u is ln of u. We're putting absolute values here just to make sure that you don't take the logarithm of a negative. Now we need to go back to x's. So this will be 2 ln of u was x squared plus 19. So it'll be x squared plus 19 plus c. I remove the absolute values symbols because x squared plus 19 is always positive and we don't need absolute values. Its ln will be the ln of a positive number. So this quantity here is always positive and you don't need absolute value symbols. Next example. You're integrating e to the power 4x over e to the power 4x plus pi. So this time we're going to let u equal e to the power 4x plus pi, denominator. Okay. The derivative of u, we're going to use the chain rule. It'll be the derivative of e to the 4x, which is itself, times the derivative of 4x, which is 4, plus pi has a derivative of 0 because it's a constant. Okay. Rearrange this so you solve for dx. dx is du over 4 e to the power 4x. Okay. So go back to the integral, e to the 4x over all of this, which was u. dx is this. dx is du over 4 e to the 4x. Okay, e to the 4x is going to cancel, and that leaves us with 4 in the denominator. Take it out. So it's 1/4 integral of 1 over u du, which is ln u. Okay, 1/4 ln u. Next, we need to substitute for u. u was e to the 4x plus pi, so it'll be 1/4 ln of e to the 4x plus pi plus c. Okay. Here's a really good example. I really like this example. And I think if you can do this 2 or 3, then you can do a lot of them. Okay. The integral of tangent to the power 5 of 2x times secant squared 2x dx. Okay, I'm going to give you a bunch of choices for u, the letter u, to simplify this integrand. First choice is let u equal secant 2x. Second choice is let u equal secant squared 2x. Or let u equals tangent 2x. Or let u equals tangent to the power 5 2x. Or let u equal 2x. Only two of them will work, and one of those two will be longer than the other one. So there's two choices that work, but one is long, one is not. The other three choices don't work. Let's think about this for a few seconds. Okay. The choice that will work is let u equal tangent 2x. Okay. The derivative of u with respect to x is secant squared 2x times 2. I'm going to stop here for a few seconds and go back to why the other choices would not work. So let's go back to these choices. Okay. Tangent to the fifth would not work because when you differentiate it, you have to use the chain rule and it makes it longer. So this is out. Same thing with secant squared. Besides, secant squared is the derivative of tangent, so that wouldn't work. Secant 2x, same thing. When you differentiate it, it makes it worse. So the two choices that would work are these two choices. But 2x will not result in much simplification. So this is why you could pick 2x, you go through all the steps, then you find yourself having to do more steps. If you pick tangent 2x, it's better. So whenever you have an exponent, don't pick the exponent most of the time. Pick the function without the exponent, like tangent 2x. So for example, if we had sine to the power 88x, don't pick sine to the power 88. Just pick sine, and that'll work. So let's go back. So we pick this. Okay, rearrange for dx. So dx is du divided by 2 secant squared 2x. And here's dx. Now substitute back in the integrand. Tangent 2x to the power 5 is u to the power 5 because tangent 2x is u. So this is why you don't, it's okay to integrate u to the power 5. Secant squared 2x is down here, and then dx is this. So secant squared x would cancel anyway. That leaves us with the 2 in the denominator. Take it out, 1/2, and that leaves us with u to the power 5 du. The integral of u to the power 5 is u to the 6th over 6. This is why it's not necessary to put exponents most of the time in u. So if u is equal to tangent 2x, that's sufficient. All right, 2 times 6 is 12, so this is u to the 6th over 12. And u was tangent 2x, so this is tangent 2x to the power 6 over 12 plus c. Let's do another example. This is also a good one. The integral of ln x over x. Well, let u equal ln x. Du dx is 1 over x. Cross multiply, so dx is x times du. This is dx, and this is where dx is. Integrate. Okay, the numerator ln x was u over x times dx, which is x du. The x is cancelled, so that leaves us with the integral of u du, which is u squared over 2. But u was ln x, so this is ln x squared over 2 plus c. Okay, we're faced with the same choices as before. Would we let u equal sine x, or cosine x, or e to the sine x? Okay, e to the sine x is going to be a chain and make the integration worse, so that's out. It's more helpful to us to let u equal sine x, so let u equal sine x. Du dx is cos x, so dx is du over cos x, that's dx. Substitute, so it'll be cos x times e to the u times dx. dx is du over cos x. Cos x cancels, so that leaves us with integrating e to the power u du. The integral of e to the power u du is just e to the u. And u is sine x. So it's e to the sine x plus c. Here's the next example. Well, here we have 3 cos x over this whole thing to the power 4. So it would be to our benefit to let u equal sin x plus 2 alone without the exponent 4 for reasons we explained before. The derivative of this is just cos x. So dx is du over cos x. That's dx. Let us substitute. So we have 3 cos x over u to the power 4. dx is du over cos x. Cos x will cancel. That leaves us with 3. Take that out. Integral of 1 over u to the power 4. The integral of 1 over u to the power 4 can be rewritten as u to the power minus 4. Integral of u to the minus 4. The 3 is out. And this integral here will be minus 4 plus 1, which is minus 3. So u to the power minus 3 over minus 3. The 3 cancels the 3. So this leaves us with a negative u to the minus 3 plus c, which is minus 1 over u cubed. And u was sin x plus 2. So it's minus 1 over sin x plus 2 all cubed plus c. I'll extend this line a little bit. Okay. We're going to do one more example. Or, yes. One more. You're integrating sine to the power 99x cos x dx. Okay, now we're used to doing these. So in this example, we're going to do it slightly differently. Okay, if we let u equal sine x, then cos x dx will be du. So think of this as u to the power 99. But the only way we could is if what follows it would be its derivative. So the derivative of sine x is cos x dx. That would be du. Okay, so all we're integrating is u to the power 99 with respect to u, which is u to the power 100 over 100. So it's sine to the power 100x over 100 plus c. Personally, I prefer to do the steps and to find dx each time. That way you can't go wrong and you can simplify. But some people choose to just write du directly or replace cos x dx directly by du, and that's fine also.